when you're looking at an integral, you're not going to know what to do. No, typically, with some exception, but typically, once you get to an exam, they'd be like, here are some integrals, find the antiderivative using whatever method works. Usually there's only one method. Occasionally there might be two different ways to go, but usually it's going to be either simplifying the expression and then antidifferentiating it, or trying a u-substitution, or trying integration by parts, or trying partial fractions. And we're going to try to kind of develop an intuition about when to try what sort of thing. So let's look at some more examples here, specifically in the context of u-substitution. So let's say we were looking at something like, well, I'll try to remember the right numbers here. The integral of the natural log of x cubed over x dx. So this is a prime example of when we would use a u-sub because I see the two things I'm looking for. I see that there is a function inside another function, and the function that's inside its derivative is also in my integral. The choice I want to make here is to let u equal the natural log of x. The reason is because my du dx, my derivative, is equal to 1 over x. Normally, I would say when we get comfortable doing this process, we typically skip writing du dx equals the derivative, and we move the dx over automatically and write it as du equal to the derivative multiplied by dx. Our job at this juncture is to rewrite this integral using no x's and all u's. We cannot have any x's. It has to be all u's. So we're going to rewrite this as, actually, I'm going to do one thing first to make it a little more obvious. I'm going to write this as the natural log of x, my x looks terrible, sorry, cubed times 1 over x times dx. It's the same thing, right? Dividing by x is the same as multiplying by 1 over x. And look, we exactly have the pieces that are over here. My 1 over x times dx is exactly equal to du. And my natural log of x is exactly equal to u. So we can rewrite this integral as the integral of u cubed du. I would encourage you all, when you do a u-substitution, make sure that dx grabs whatever it needs to go along with it and turns into du before you do anything else. So don't start changing this natural log of x into u until after you've made sure the dx turns into du. But the dx has to grab the pieces it needs to go with it. After this, the point is this is supposed to be easier. Right? We know how to integrate u to the third or x to the third. We just add 1 to the power divided by the new power. This is going to be u to the fourth divided by 4. Make sure your 4's and your u's look different, plus c. We're not done, right? Our initial question was to find the antiderivative of natural log of x cubed over x, or the indefinite integral. Our answer should be a function, and it should be a function of the same variable that we started with. So if you're doing an indefinite integral and you're starting with x, you have to end with x. So we're going to rewrite this by just replacing u with the natural log of x as the natural log of x to the fourth divided by 4 plus c. I'm going to remind you, when you're doing a u-sub, what you're really kind of looking for is you're looking for the inner function in a chain rule. Right? If I take just to kind of show you the reverse process here, if we take the derivative of this antiderivative, the derivative of, I'm going to write this as 1/4 times the natural log of x to the fourth plus c. Well, the constant multiple hangs out. The derivative of a function to the fourth power is 4 times that function to the third power multiplied by the derivative of the inside function because of the chain rule, plus the derivative of constant 0. So, right, so we were really looking for the inside function whose derivative also comes up when we use the chain rule. And then we simplify this and you exactly get 1/4 and 4 cancel. You get the natural log of x cubed over x. You don't have to check this. I'm just pointing out that if we reverse the process, we should end up back where we started. But really, I'm trying to point out more that what we're looking for. We're looking for the inside of the chain rule that we let u equal. Let's look at some, I should pause. Let me pause and see if you have any questions. Okay, so let me have you all try this next example. I want you to find the antiderivative of 3 plus sine of x to the fifth power times cosine of x dx. And I think I've written in such a way that there should be what seems like an obvious choice for you. So try that one on your own. I'll give you a couple minutes. It's been a minute and a half, so it's as long as I can wait. All right, so I think obvious choice here is to let u equal 3 plus sine of x, again, for the two good reasons. It's stuck inside another function. It's being raised to the fifth power. Also, the derivative of 3 plus sine of x is exactly cosine x. So our du is equal to cosine of x multiplied by dx. So we can exactly replace this cosine of dx with just du and this 3 plus sine x with just u. So we're getting the integral of u to the fifth du. We're getting 1/6 u to the sixth plus c, and then we're rewriting it as 1/6 times 3 plus sine of x to the sixth plus c. I mean, we're not going to do it, but you can see that if we took the derivative of this, the 6 would come down, the new power would be 5, you'd have 6, or I should say 1/6 times 6 times this to the fifth, multiplied by the chain rule, the derivative of 3 plus sine x, which is the cosine x that's right there. Okay, now we're not always going to be quite so lucky in that it's not always going to be exactly your u is going to be, its derivative is perfectly going to be there. Let's look at this next example. Let's say we're going to find the integral, where'd you go? Not you. Yeah, sure, you. X to the fourth times sine of x to the fifth plus 2. Your intuition should still be telling you what your u is here. The u is the thing that's stuck inside another function. So I'm definitely thinking that my u is x to the fifth plus 2, which it is. I should say you can pick anything for u. It just depends if it's going to work or not. One thing I'll point out, if you're trying a u substitution, you should never pick for u, x. Because picking u equal to x really just means you're rewriting the integral with u's instead of x's, but it hasn't changed yet. I will counter that with, if you're doing integration by parts, it's perfectly valid to sometimes let u equal x. So in a u sub, u equals x is you're just not getting anywhere with u equals x. Like if I let u equal x right here, my du would be dx, and my new integral would be u to the fourth times sine of u to the fifth plus 2 du. It hasn't changed. It's still the same. So just a word to the wise. Here, I should find my du. My du is the derivative of this, which is 5x to the fourth times dx. And I don't exactly have that, but that's fine. As long as we are off by just a constant multiple, we can always fix that. So I saw x to the fifth, and I saw essentially the derivative of x to the fifth, which is something times x to the fourth, and I was happy about that. I was happy that, oh yeah, the thing inside was a one higher power of x than the thing over here. So as long as you're off by a constant multiple, it's not a worry. There's a couple different ways to go about doing this. My preference is to say, look, in my integral, I have an x to the fourth times dx. So I would like to make this thing over here look like an x to the fourth times dx. So I'm going to multiply both sides by 1/5 and say that 1/5 times du is equal to x to the fourth times dx. You don't need to, but I often think it's convenient to rewrite this so that things are next to each other. Again, not at all necessary, but if you really, really want to, you can rewrite this as sine of x to the fifth plus 2 times x to the fourth dx. And then say, okay, great. This x to the fourth dx is our 1/5 times du. And this x to the fifth plus 2 is our u. And this pen is dying. Okay, so I'm in the red pen. Yeah, but this one, I feel like this one's dicey. Yeah, it's not great. Okay, anyway. All right, so then we're going to just rewrite it as the integral of sine of u times 1/5 du. Now, one thing I'll point out, if you have something times du that's going in for your whatever dx, it is almost always the case that we just put the 1/5 out in front. Whatever the multiple of du is, any constant multiples inside an integral, it is usually easier if we just put them out in front. So I would rather write this as 1/5 times the integral of sine of u du. We integrate, we get 1/5 times the antiderivative sign is negative cosine. So I'm going to write something kind of wrong for a second. So if you write it like that, even though you might mean multiplication, it looks like I've written 1/5 minus cosine of u. If I want to write 1/5 times negative cosine of u, you really shouldn't use a dot. You should really use a parentheses here. So I should say 1/5 times negative cosine of u. And then what I should really do is write the negative out in front. So this is really equal to negative 1/5 cosine of x to the fifth plus 2 plus c. So I want to stress to you all, when you're making a choice for u, you want it to be typically the thing that's inside another function. Generally. So I should say, anything we say in this class, it's like, when I say something is what you want to do, that's probably true most of the time. But occasionally there's going to be some corner cases where it doesn't always work that way. So most of the time, if you're thinking u-substitution, you want the thing you're picking to let u equal to be something inside another function. And more importantly, we hope that its derivative is also present somewhere. So let's look at a couple more examples. Sure, yeah, that's fine. So let's say we have the integral of x plus 5 divided by x squared plus 10x plus 3 to the fourth. So I think this is a good. So I want to point out, even if there wasn't a fourth power there, if it was just x plus 5 over x squared plus 10x plus 3, x squared plus 10x plus 3 would still be a good candidate, even though it kind of doesn't have the appearance of being stuck. It's still stuck. It's in the denominator. If something's just in the denominator, you could always write it as multiplication by that thing to the -1 power. And then you can kind of see, oh yeah, that thing is inside another function. So here it definitely seems plausible to let u equal x squared plus 10x plus 3. It might not work. Sometimes sometimes you're going to try u-sub and it's not going to work. Get comfortable doing the wrong thing first. It's going to happen. It's okay. Then you try something else. But let's see. So here our du is going to be the derivative of this, which is 2x plus 10 multiplied by dx. You don't really have to write parentheses around your 2x plus 10 here, but it doesn't hurt to. I don't have a 2x plus 10 times dx, but I do have a multiple of that, right? Definitely my x plus 5 times dx is going to work out. So let's a different color over here. I got purple. Let's use purple. This x plus 5 times dx, well, if I multiply both sides of this by 1/2, 1/2 times du is equal to 1/2 times 2x plus 10 times dx, which is exactly x plus 5 times dx. Yeah, that's really how I would do it. So then we can rewrite our integral. So the x plus 5 times dx gets replaced with a 1/2 times du divided by u to the 4th. You can put the du on top of your fraction or onto the side of your fraction. It doesn't actually really matter where you put it, just not in the denominator. So I'm going to rewrite this as 1/2 the integral of u to the negative 4th du. We're going to anti-differentiate. We're going to get 1/2 times u to the negative 3rd divided by negative 3 plus c, which is then going to be negative 1/6 times my u, which is x squared plus 10x plus 3 to the negative 3rd power plus c. Exciting. So I would say your intuition should always kind of be on the lookout for, is there something inside some argument or some function here? Is it sensible to try letting u equal that inside part? If I let u equal that inside part, does the derivative of that also show up somewhere else in my integral? That's what we should be thinking if we're thinking u-substitution. And to be honest, here's what I'm going to say. When I'm integrating something, my first thought process is, can I do a u-sub? I should back up. My first thought process is, can I simplify this thing to make it just easy to do? And then if that doesn't work, my first method, my go-to method is like, can I do a u-substitution? That is usually the easiest way of integrating something. Let's look at a few more examples. Sure. Let's say we have, let's see if I can keep the numbers going. I always stop writing the numbers after a while because I just forget. Let's say we have the integral of, sure, secant squared of x times e to the 4 tangent of x dx. Okay, write down your choice for u. I'm going to pick 4 times tangent of x for my u. So then my du is going to equal 4 times secant squared of x times dx. And oh, look, we happen to have that. How convenient. Well, almost, right? I'm off by a multiple of 4. So I would always prefer to make this thing look like what I have, but other people do this slightly differently. I'll point out just a slightly different way of doing this. Other people might say, I'm going to rewrite my integral by multiplying by 4 and by 1/4. So I can rewrite this as 1/4 times the integral of 4 times secant squared of x times e to the 4 tangent of x times dx. That is equally valid. And again, we see, oh, look, here and here, right? You definitely need to make sure the dx is getting counted as being necessary for your du transformation. Those two pieces are giving us our du, right? Du is 4 times secant squared x times dx. So we can rewrite this integral as 1/4 times the integral of e to the u times du. I will point out because I can't help myself really. You could also do it the way I would prefer to do it, which is to say 1/4 times du is equal to secant squared of x times dx. And then you would say, sorry, from here, let me just do this instead. You would say, okay, my integral of secant squared of x times e to the 4 tangent of x dx. Well, the secant squared of x times the dx, that's giving me my 1/4 du. And then this is going to equal the integral of e to the u times 1/4 du. It's the same, just the 1/4 is in a slightly different spot. Either way, when we anti-differentiate this, we get the same thing, right? What's the antiderivative of e to the u? It's e to the u. So we get 1/4 e to the u plus c, and then replacing u with what it's equal to, we get 1/4 e to the 4 tangent of x plus c. And if you took the derivative of this, you would get 1/4 times e to the stuff multiplied by the derivative of that stuff, which is 4 secant squared of x, and the 4 and the 1/4 cancel. You get exactly that. I wouldn't encourage you to actually write down the derivative of your answer, but I would definitely encourage you to think about, if I took the derivative of this, would I actually get the thing back here? If you're using u-substitution to find the answer, you should be having to use the chain rule to take the derivative of your answer. All right, let's look at at least one more u-substitution. And then we'll say some other things. Time. So little time. Let's say we want to find the integral of sine of the square root of x divided by the square root of x. So it seems like there's probably an obvious choice for you here. I would imagine it was u equal to the square root of x, which I would probably prefer to write as u equal to x to the 1/2. And my du is 1/2 x to the negative 1/2 multiplied by dx. I don't like to write it this way because I feel like it doesn't help me out as much as writing it as du equal to 1 over 2 times the square root of x dx. And at this point, I'm going to pretend like I forgot the things I've said. Meaning, normally I would point out that we need to make sure that dx turns into du first. But if we forget that for a minute, look where you can, here's how you can go wrong. So you might not want to write this down actually, but here's the wrong way to go just for a second. If I'm not paying attention, I might say, well, look, my integral of sine of root x over root x times dx, well, root x is u, so it looks like I've got sine of u over u, and then if I'm not paying attention, I might just be like du, sure, why not? No, right? That's a problem for two reasons. One, I'm literally left the sine of u over u times dx, and then I don't really have a good way of turning dx into, dx is du times 2 root x. That's not super helpful. You can make it work if you go that way, but it's not what I would recommend. So really, I want to point out that you really have to be extra careful about making sure before you start replacing the things that look like u with u's, you have to make sure you use whatever pieces of them you need to rewrite du in terms of dx. So not this. What we should have done is hey, look, my du is equal to 1 over 2 times the square root of x times dx, and I have a 1 over square root of x times dx. So I'm going to rewrite my du, I should say, I'm going to reformulate this equation, multiplying both sides by 2. 2 times du is equal to 1 over the square root of x times dx. So then I can rewrite this integral as the integral. I'm going to rewrite it in the following way as sine of root x. Instead of divided by root x, I'm going to say it's multiplied by 1 over root x times dx. And then I can observe that, yes, this part here, this 1 over root x times dx, that is equal to 2 times du. And only this root x gets to turn into u. This other root x, we needed it to go with the dx so that we could get our du showing up. So then we can rewrite this as the integral of sine of u, and I'm going to be smart here. Instead of writing times 2 du, I'm going to put the 2 out in front and just say times du. Not super important, but usually we do that. And then we're going to integrate. Again, the integral of sine is negative cosine of u. So instead of writing 2 times negative cosine, let's write negative 2 times cosine of u plus c, and then negative 2 times cosine of the square root of x. 137. Okay. Sure. Oh, that one's always fun. Yeah. Yeah, we'll do one more. We should start talking about integration by parts because, yep. So, oh, that was number 6. That was number 6, right? Number 6, probably. Yeah. All right, so let's look at this next one here. We're actually going to look at 2 different problems at the same time. We're going to get the integral of e to the 2x over 1 plus e to the 2x. And then after that, we're going to look at the integral of e to the x over 1 plus e to the 2x. Don't forget your dx's. They're vital. All right, so again, if we're coming at this with kind of like a blank slate, I'm going to try a u-sub, and I'm going to let u equal the stuff that's stuck inside the bottom. So here, I'm going to let u equal 1 plus e to the 2x. My du is going to be the derivative of this. So the derivative of 1 is 0. The derivative of e to the stuff is e to the stuff times the derivative of the stuff, which is e to the 2x times 2. And then we multiply by dx. That looks pretty good, right? I've got an e to the 2x times dx. I can make the right-hand side of this an e to the 2x times dx. So we have 1/2 du equals e to the 2x times dx. And then we can rewrite this. That part there is going to be our 1/2 du. This part down here is going to be our u. So we're going to rewrite this as the integral of 1/2 du over u. I probably should put the 1/2 out in front. One thing I want to point out is people will often write integrals like this as the integral of du over u. Some people find that confusing. If you don't love that, I totally understand. You can rewrite it as 1/2 times the integral of 1 over u times du. It's the same thing. But writing it like this, I feel like makes it a little bit more obvious that we're anti-differentiating 1 over u, and the antiderivative of 1/2 times 1 over u is 1/2 times the natural log of the absolute value of u. And then we're going to plug u back in, or substitute u back in, and get 1/2 natural log of the absolute value of 1 plus e to the 2x plus c. Side note that's not that important here, but in case you were looking at this problem in the textbook solutions, you might see in the solutions that they write their answer as 1/2 natural log of parentheses of 1 plus e to the 2x plus c. The first way of writing it is totally correct. And in this particular example, the second way is also correct because the argument of the logarithm, 1 plus e to the 2x, is already always positive. So taking the absolute value of it doesn't change it at all. So if you happen to have something inside an absolute value of a logarithm, inside the absolute value that's inside the logarithm, that's already always positive, sometimes people will just drop the absolute value. So if you've ever seen someone integrate something and get natural log of absolute value of whatever, and then drop the absolute values later on, it's typically because the inside part is already always positive. So just so you're aware. Again, totally unnecessary. So if you're doing this kind of work and you get your integral is the natural log of something, and then you have this, make sure you just leave the absolute values. It's always going to be correct if you leave the absolute values. Right? When you integrate 1 over u, you get the natural log of the absolute value of u. When you integrate 1 over x, you get the natural log of the absolute value of x. I will point out, just to make sure everyone's cool and aware, we didn't have an absolute value here. You don't get an absolute value every time you have a natural log of x. You only get an absolute value when you anti-differentiate 1 over x and get the natural log of the absolute value of x. Here, it just showed up because it came back into our formula later on. Okay. On the other hand, the second problem, well, you can kind of even see, if we let u equal 1 plus e to the 2x, our du is e to the 2x times dx times 2. I don't care about the 2. And I don't have that here. I don't have an e to the 2x times x dx. I have an e to the x times dx, and that's a whole different animal. So in this problem, it's less obvious what the choice for u is. So if you have to choose between picking a thing that's stuck inside another function or picking a thing whose derivative is already in there, usually the second thing, picking a thing whose derivative is already there, is the better choice if you can make that happen. So I see that I would like my derivative to be e to the x times dx. So I'm going to pick u equal to e to the x because my du is e to the x times dx. And just like the other problem with the cosine of the square root of x or sine square root of x, I don't just want to start putting in u's where all of a sudden. I want to first make sure that e to the x times dx turns into du. So this e to the x times dx has to become my du. I should mention, it's totally okay to write your integral with x's and u's. You just can't stop there. So it'd be totally fine for me to write this as the integral of du over 1 plus e to the 2x. If I didn't know exactly what to do with the bottom from the get-go. But then I have to keep going. I'm going to write this as the integral of du. Okay, here's the trick for this one. E to the 2x is really just e to the x to the second power. Right? Power to a power, you multiply the powers. E to the x squared is e to the 2 times x, which is that. And then e to the x was our choice for u. So we can rewrite this as the integral of du over 1 plus u squared. Duh. Clearly, I don't like writing the du on top. I would prefer to write this as the integral of 1 over 1 plus u squared du. This is one of those functions we're expect to recognize as the derivative of a known thing. The antiderivative of 1 over 1 plus u squared is the arc tangent of u. And finally, we plug back in u, and we get the arc tangent of what u is equal to, which is e to the x plus c. Yeah, we should do all the things. Okay, so let's look at that. Let's look at that. So let's see here. Problem 9. Yeah, we'll do this one. So let's say we have the integral of, sorry, 1 second. Let me think. Oh, this should be fine. 1, 2, sure. Of the x squared times the square root of, sorry, brain of x cubed plus 1 dx from 0 to 2. So a somewhat different problem for us in that now, instead of just having an indefinite integral, we have a definite integral. That's still going to need a u-substitution. So the choice for u is not terrible. We're going to pick u equal to the stuff inside the square root for both reasons, because it's stuck inside the function and its derivative is already there. Our derivative is 3x squared, and we multiply it by dx. And we've almost got that. So I'm going to write this as 1/3 times du equal to x squared times dx. I will point out some people, not me, like to do a thing where they isolate dx completely. Some people would like to go ahead and say du divided by 3x squared equals dx, and then replace the dx with that, and then cancel the x squared. That's also a fine way of doing it, as long as things work out nicely. But if they don't work out like in this way where the derivative is exactly showing up, kind of, it's less good. I know that doesn't sound very specific, but it's harder to make things work out the right way if it doesn't go exactly as planned. So I don't prefer this, but you're not me. You should do whatever works best for you. Okay, so I'm going to rewrite this integral. My dx times x squared is going to be my 1/3 du. So I'm going to rewrite this as the integral of, hold off on the limits of integration, my 1/3 times du. And here I have the square root of u. Now we should talk about the limits of integration. So we have done a substitution or a transformation of our variable. This integral said we want to find the area under this curve from x equals 0 to x equals 2, which is equivalent to finding the area under this curve from whatever u equals to whatever u equals. So if x is equal to 0, u is equal to 0 cubed plus 1, which is 1. And if x is equal to 2, u is equal to 2 cubed plus 1, which is 8 plus 1, which is 9. So our new limits of integration are from 1 to 9. This is the way I would encourage you all to do a problem like this. So if you have a u-substitution with definite integral, I think it's best to change the limits of integration to your new variable. But I'll show you how to do it the other way if you don't want to do it this way. So then I'm going to rewrite the square root of u as u to the 1/2. So it's 1/3 times the integral from 1 to 9 of u to the 1/2 du. We end up getting 1/3 times, we're going to do u to the 1/2 plus 1 is 3/2. And then instead of writing divided by 3/2, we know that when we divide by a fraction, we multiply by its reciprocal. So instead of dividing by 3/2, we're going to say we multiply by 2/3. Evaluated from u equals 1 to u equals 9. So that's going to be, let's see, 1/3 times 2/3 is 2/9. First, we plug in the 9, and we get 2/9 times 9 to the 3 halves minus 2/9 times 1 to the 3 halves. So that's going to be 2/9 times, let's see, 9 to the 3 halves is 9 to the 1 half, which is the square root of 9, which is 3, and then 3 cubed, which is 27, minus 2/9 times 1. So that's going to be 54 minus 2 is 52/9. Alternatively, if you do not want to change your limits of integration, you, from this juncture here, you can say, well, I'm just going to leave them alone. But here's the deal. If you write this, some people might dock you some points for that. Because technically that's wrong, right? U isn't going from 0 to 2, X is. So I usually, what I would do if I was trying to do it this way, is I would write X equals 0 to X equals 2. So that the person grading your work still knows that you know that those are X values, not U values. And then we're going to do the same work. We're going to get 1/3. We already know the antiderivative of U to the 1 half is 2/3 U to the 3 halves. So we get 1/3 times 2/3 times U to the 3 halves. And we're evaluating this from X equals 0 to X equals 2. And then since we're keeping it in terms of X, we have to go back to being in terms of X. So we're going to write this as 2/9 times X to the 3rd plus 1 to the 3 halves power, evaluated from X equals 0 to X equals 2. And now we can plug those in and we get 2/9 times 2 cubed plus 1 to the 3 halves power minus 2/9 times. Here's a good example of plugging in 0 doesn't give you 0. If you plug in 0 here, you get 0 cubed plus 1 to the 3 halves power. So I want to, just since I saw the opportunity there, want to remind you all, you don't always get 0 when you plug in 0, right? You actually have to look at what you were plugging it into to make sure. Oh, look, this is the same. This is 2/9 times 9 to the 3 halves power minus 2/9 times 1 to the 3 halves power. So either way you do it, you should end up at the same place eventually. Just depends on how you want to write your work. I obviously, hopefully it's obvious, I think doing it the first way is better. But if you like to do it the second way, that's also okay. All right, let's go ahead and in the last 10 minutes here, talk about integration by parts. Integration by parts. Almost always abbreviated as IBP. How much do I want to say about integration by parts? Good question. So the idea is we would like to be able to integrate something like 2x times cosine of x. And the problem is you cannot just anti-differentiate the things multiplied together and multiply the results together. Or in other words, this is definitely not equal to x squared times sine of x. Even though the antiderivative of 2x is x squared and the antiderivative of cosine x is sine x. Why is the integral of this not equal to this? Say that again? The product rule, exactly. Because if you take the derivative of this, the derivative of x squared times sine of x requires the use of the product rule, which is going to be 2x times sine of x plus x squared times cosine of x. And that is certainly not equal to 2x times cosine x. So a good sign that you might need to use integration by parts is you have two pretty distinct things multiplied together. And typically, it's not like a very complicated inner part of that function. Like it's not looking like it may be a u-sub where the argument of your function is more complicated. So how does this work? Well, it really does come actually from the product rule. So yeah, let's just try and write this the most easy way possible. So I'm going to write the following here. So here's where the integration by parts formula comes from. If you take the derivative of u times v, using the product rule, and we use u and v, I don't know why, because someone is a masochist and wanted to penalize people whose u's and v's don't look that different. So make sure your u's and v's look different enough, because otherwise it's really easy to mess things up. I don't know why they chose u and v, but they did, and it's what we use. So God help us all. So you're going to get the derivative of u times v plus u times the derivative of v, which Now we're going to anti-differentiate both sides of this. The antiderivative of a derivative is just the thing you started with. So if we anti-differentiate both sides, we're going to get just u times v on the left. And I'm going to write this other side slightly differently. So I'm going to write this as the antiderivative of, instead of u prime times v, v times u prime, but I'm just going to write u prime as du. So there's my u prime. We're writing it as du. In a similar way, we're going to write this as plus the integral of u times dv instead of writing v prime. And then we're going to isolate this one. So we're going to say that the integral of u times dv, and I know I'm putting it on the other side, but bear with me. So this integral is equal to u times v minus that integral, v times du. That is your integration by parts formula. Some people like to say ultraviolet for the UV, like UV rays, super voodoo for the VDU, for the integral of VDU. The super looks like an S, the voodoo is the VDU. So ultraviolet super voodoo, you might think you can forget it. I've never been able to forget it. I've tried so hard, won't leave my mind. So ultraviolet super voodoo is our formula for integration by parts. But what's the whole point here? The point is we're going to look at our original integral. We're going to make choices with the goal that the new expression, which is still going to have an integral in it, the new expression's integral is easier to deal with. Almost all the things we do in this class, as far as integration is concerned, is trying to make the integral easier so that it looks like something we actually know how to deal with. So looking back at this example here, the integral of 2x times cosine of x dx. I know that I could put that 2 out in front, but I'm not going to because I don't want to. So the idea here is that you want to pick a u and a dv. Really, you want to pick a u, and then the rest of it's going to be dv. And our guidelines for picking u are different than they were before. It's not like a u-substitution. Here, the way you want to pick u is you want to pick u to be something that's derivative is much nicer than the original function. So the primo candidate for u is the natural log of x. Natural log of x is a pain in the butt. Its derivative, though, is just 1 over x, which is x to the minus 1, which is relatively simple. So kind of the order of best picks for u is first pick u equal to a logarithm, if you've got one. Typically natural log, but it could be log base 3. Not usually, though. If you don't have a logarithm, then you want to pick u equal to, people like to say an algebraic term. I like to say any power of your variable, and usually x, but whatever your variable is. So like x to the third, x to the fifth, the square root of x, which is x to the 1/2, 1 over x, which is x to the negative 1. Those are all great choices for your u because their derivatives are relatively not terrible. And then finally, you might, if you don't see a log or an algebraic term or any power of x term, you pick u to be a trig function like cosine of x. And if you don't have any of those, well, you probably will if you're using integration by parts. We write e over here just because like the end of the word, e to the x, but really you're almost never picking u equal to e to the x in an integration by parts problem. Because the whole point here is that the u thing should be a thing that's derivative actually gets simpler, like a lower power or a nicer function, whereas your dv thing should be something that when you anti-differentiate it, it doesn't get worse. And e to the x is kind of like the best thing to anti-differentiate because it doesn't get worse. It stays the same. Sine and cosine are also good choices to anti-differentiate because they stay pretty much the same. The antiderivative of cosine is sine. The antiderivative of sine is negative cosine. So not too bad. So here, we're going to pick u equal to 2x. And dv is the rest. dv is cosine of x multiplied by dx. And if you imagine multiplying u times dv, it better be exactly what's in your integral. So things need to be appropriately in the numerator or denominator. And then we're going to write down the rest of what we need. So we need the du. So du is just the derivative of u times dx. So the derivative of 2x is 2 times dx. And our v is going to be the antiderivative of dv. So the antiderivative of cosine is sine of x. And then we're just going to toss all of this into the formula uv minus the integral of v du. So we're going to rewrite this as being equal to u times v. We don't actually write u times v, though. You just write what u is equal to times what v is equal to. So it's 2x times sine of x plus the integral of v times du, bless you, sine of x times 2 times dx. And look, our new expression, the integral in our new expression is something we can actually deal with. We know how to find the antiderivative sine of x. So then we can continue on and say, great, our answer is 2x times sine of x plus 2 times the integral of sine, which is plus 2 times negative cosine, which is minus 2 times cosine of x. Instead of writing plus 2 times negative cosine of x. That's our answer. It wouldn't surprise me to see a question on your first exam, something like, and I think someone will show me a homework question like this maybe, that says something like the integral of 2x times cosine x is this. Show it's true by taking the derivative of this and getting that. So if they're asking you if an integral equal to something else is actually true, the point of that question is not to actually do the integration. The point of that question is to take the derivative of your integral and see if you get back to where you started. So if how much time have I got here? Yeah, not long. So if I asked you the question, sorry, that's a little fast. If I asked you, is the integral of x cubed e to the x dx equal to x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x plus c, you would not check it by doing the integral. For those of you, if you're curious how I did that, it's a trick. I'll show you later. But the way you would check that is by taking the derivative. So the derivative of x cubed e to the x minus 3x squared e to the x. I should be smarter about this. Plus 6x e to the x minus 6 e to the x. I'm going to leave off the plus c because I know the derivative of plus c is 0. I don't want to use the product rule 1, 2, 3 times. And I shouldn't, because I can see that each of these things I could factor out the e to the x. So if I was being smart about this, I would rewrite this as the derivative of x cubed minus 3x squared plus 6x minus 6 times e to the x and use the product rule on that. So the derivative is going to be 3x squared minus 6x plus 6 times e to the x plus x cubed minus 3x squared plus 6x minus 6 times the derivative of e to the x, which is also e to the x. Then you can factor out the e to the x's and you get, check it out, 3x squared minus 6x plus 6 plus x cubed minus 3x squared plus 6x minus 6. And look, the things cancel. 3x squared, negative 3x squared, negative 6x, positive 6x, plus 6, minus 6. And you get exactly x cubed e to the x. So that shows us that this integral must equal that because the derivative of that was equal to the integrand x cubed e to the x. Cool. We'll talk more about this on Friday.